Welcome to lecture number 15. Today we are going to study two-photon state produced by parametric down conversion. This is a second order nonlinear optical process that produces two photon, in fact the two entangled photons. But before we get into that, let's look at what we did in lecture number 14. So in lecture number 14 we looked at the basics of nonlinear optics, and we looked at the concept of polarization, which is connected to the electric displacement through this expression. Here D is epsilon naught E plus P is the electric field, D is the electric displacement vector, epsilon naught is the permittivity, vacuum permittivity, and P is the polarization, which is the dipole moment per unit volume. Dipole moment gets induced when an atom is placed in an external electric field. And as we saw, when the atom is placed in an external electric field, the negatively charged electron cloud gets pushed by the field, and as a result the center of the negatively charged electron cloud is no longer coincides with the positively charged nucleus. And as a result we have the situation where we have this positive and negative charge separated by some distance d, and this induces causes a net dipole moment per atom, and the dipole moment per unit volume of the medium is what's called the polarization. So when the applied field is not very strong, and that's when a medium acts as a linear medium, the restoring force on the electron, and thus the dipole and polarization, they are all proportional to d and thus to E. But when the applied field is quite strong, and then the medium starts acting non-linearly, and at that point the dipole moment and the polarization, it is no longer just proportional to d. So in addition to polarization having a term that is proportional to E, it also has terms that are proportional to E square, E cube, and so on. Similarly, as a result, the displacement vector will have an expression that will have terms that are proportional to E square and E cube and so on. And we saw that chi2, the proportionality constant, is the second order susceptibility, chi3 is the third order susceptibility, and so on. A material can have chi2 and need not have chi3, and it can have chi3 and need not have chi2. So it all depends on what is the symmetry that the material or medium has, and that will decide as to what non-linear susceptibility it has and which non-linear susceptibility it doesn't have. Even these non-linear susceptibilities that it has, which one is bigger, which one is smaller, and so on. So we then also looked at the second order, few second order non-linear optical effect, and for that we just considered a field which consists of two separate frequencies, omega 1 and omega 2. So that's the applied electric field, and for this applied electric field we looked at what is the second order polarization or the second order contribution to the polarization. So this is the expression of polarization, that's the linear term, that is the second order term, that is the third order term, and so on. So we just looked at what happens to this second order term when we have a field that consists of two separate frequencies. So now this actually consists of a total of 16 terms. These terms are frequency independent, and then we saw that we have these terms that have frequencies that are twice that of the external electric field. So this was the external one was omega 1, omega 2, and now we can see that this field component is at twice omega 1 and this one is at twice omega 2. So this is called the second harmonic generation. That means by having a field at omega 1, we can actually produce field at twice omega 1. And in fact, this is quite often used in several applications, including laser pointers and so on, the second harmonic generation. Then we have this term which is the sum of the two frequencies, omega 1 plus omega 2, and this is called the sum frequency generation. We also have the term which is the difference of the two frequency, and this is called the difference frequency generation. So because of this non-linear effect, the second order non-linear effect, even though the external field has only these frequencies, the second order effect causes these new frequencies to get generated, and the new frequencies are twice omega 1, twice omega 2, omega 1 plus omega 2, and omega 1 minus omega 2. Now we looked at this difference frequency generation in a little more detail, and we saw that there could be two ways of producing this field. One is when one has both this omega 1 and omega 2 present, then one can definitely do omega 1 minus omega 2, and that's a very efficient process. But even when we have just one of the field present, just omega 1, one can still produce the difference frequencies, and that process was called the parametric down conversion, and today we are going to study that in detail. So this is the parametric down conversion process, in which a medium absorbs a photon, this is called the pump photon, at frequency omega 1, and then produces two photons, one at frequency omega 2 and the other one at difference frequency omega 3. So omega 3 has to be omega 1 plus omega 2. Now parametric refers to the fact that energy remains conserved during the process. There are non-parametric processes as well, and those are non-energy conserving processes, but in this course we are concentrating only on the parametric process. So the very fact that the frequencies, the difference frequency is generated by just omega 1, the explanation is in terms of the vacuum modes, and this can only be done and proved using quantum formalism, and that is what our aim is here, that we want to derive the state produced by down conversion using quantum theory. So for that we will first derive the Hamiltonian corresponding to this process, and then the state that gets generated as a result of that. So again, let me just quickly mention here that in this process, since this is stimulated by vacuum, one can have any omega 2 here generated, and of course one can have any omega 3 value. The only constraint that one has here is that omega 2 plus omega 3 has to be equal to omega 1. So now let's derive the state that gets produced. So first of all, let's just write the expressions for polarization and displacement vector that we have for the when in the case of nonlinear optics, that's the polarization, and here we have written only up to the second term, so that's a linear term, that is the second order term, and as a result the displacement has, this is the linear term and this is the second order term. Of course there are other terms, but we are only interested at this point in the second order effects, so that's why we are writing it only up to the second order term. So this we have already derived. So that's a polarization, that's a displacement vector. Now the total energy density of the electromagnetic field, and the total means the electric plus the magnetic. So the total energy density of the electromagnetic field, this is given by D dot E, this we know. And so this D dot E, given this expression for D, can be written like this. So that's the linear term, and the corresponding to that we have epsilon naught E plus epsilon naught chi E dot E. And then because the second order term, we have epsilon naught chi 2 E square dot E. So that's the to the second. Of course there are other terms, but at this point we are not interested in those. So this is the total energy density, but this one is the energy density or the electromagnetic energy density due to the linear term. This one is the electromagnetic energy density to the second order nonlinear term. Of course there are higher order terms. So now the total energy due to the second term, that we can write now as just integrating this energy density over the volume, and the volume here would be a nonlinear medium, whatever is the medium over there. So this is the contribution to the total electromagnetic energy due to the second order term. Okay, so now that we have this the contribution to the total energy, we will try to derive the Hamiltonian from here. So now for parametric down conversion, this contribution can actually be written as this. Of course there are three fields here, E square and E, but in down conversion we have these three separate fields, pump, signal, idler. So for parametric down conversion, this contribution actually can be written like this. So we have chi 2, EP, ES and EI. So this is the energy, and in quantum formalism we basically take this energy and turn it into interaction Hamiltonian by replacing these fields by field operator and this energy by the Hamiltonian operator. So this, in the quantum formalism, this H becomes Hamiltonian operator, and these fields, the pump, signal, idler, these becomes the pump, signal and idler field operators. and as we did in lecture 12, these field operators can be written in terms of the positive and negative frequency parts. And this again, as we discussed, this is pretty much same as writing things in terms of the analytic signal representation, and this has its own set of benefits in terms of when we do it in quantum. This has its own set of benefits that the math becomes very easy when we do it in terms of the creation and annihilation operator. So we will write these fields, the field operators, in terms of the positive and negative frequency parts. So if you do that, this expression for Hamiltonian becomes this. Here we are just replacing EP, ES, EI by these expressions. So this is 2 is a total of 8 terms that we will actually get here, and all kinds of combination will have EP plus, ES plus, EI plus, and so on. But it turns out that the contribution due to the 6 terms get actually averaged out when the interaction Hamiltonian is integrated over time. So when we are calculating the state, that will involve that we integrate this Hamiltonian over some interaction time, and at that point the contribution due to 6 of these terms will actually become 0. So we are just neglecting those contribution here itself. So what we are effectively left with is are just 2 terms. The first one is EP plus, ES minus, EI minus, and this Hermitian conjugate. So that is the effective interaction Hamiltonian for parametric down conversion. So now we at this point we will only be interested in the down conversion process, where the down conversion happens in the fixed direction. That means signal idler photons only come out in fixed direction. Of course, it can be much more general that the photons can come out in any direction, but we will be first interested in the temporal effects with these 2 photons. So we are interested at this point in down conversion only in fixed direction, and we'll also fix this direction to be the z direction at this point. And with that, this effective interaction Hamiltonian can be written as this one-dimensional integral over z. And when we do this the generic problem, then we will use this generic expression. So for the down conversion process in which the photons come out in fixed directions, that becomes the effective interaction Hamiltonian. Okay, now we now want to write these electric field operators, and these electric field operators, as we discussed in lecture 13 or so, can be written like this. Here we are just writing this field in time in terms of the operators in frequency. So this mode expansion is exactly how we do things in the classical optics. There is really no difference, except that the field amplitude gets replaced by creation or annihilation operator. Otherwise, this mode expansion remains exactly same in classical and in quantum description. Now, in addition, let's point out that here we will be treating the pump field classically, and that's why we are not writing it as a annihilation operator. It's just the field amplitude that we have here, and this is because the pump that we use here is usually a laser which is of tens of milliwatts or 100 milliwatts or so, and 100 milliwatts means lot of photons. So we don't need to treat the pump quantum mechanically, although one can actually treat it quantum mechanically, but we can actually as well treat it classically, and that will make the math much simpler. But the signal idler photons, there is only one or a maximum of 2 of them. There's one signal, one idler, or we can have some probability where we have 2 signal or 2 idler. In fact, we will not even be looking at those possibilities. So the kind of effects we are interested in, kind of intensities we would be working at, we will have at most 1 signal and 1 idler, and hence we need to treat them quantum mechanically. So that's how we have expanded our 3 field operators. And so now if we put in these expression into this Hamiltonian, this is what we get for the Hamiltonian interaction Hamiltonian for the down conversion process. So that's this term plus this Hermitian conjugate. So now that we have derived the Hamiltonian, we want to derive the state that gets produced by the parametric down conversion. So here we have this crystal of length L, and this pump photon comes in and hits the crystal, let's say at time t equal to minus t interaction, and it reaches the other end at time t equal to 0. And then we want to see that during this interaction, what exactly is the state that gets produced here. So here we assume that the pump photon starts interacting with the crystal at time t equal to minus t interaction, and the state of the down converted photons at t equal to minus t interaction is given by just vacuum signal, vacuum idler, because at t equal to t interaction, minus t interaction, the pump has just started interacting, hence there is no photons, there is no signal, the parametric down conversion has not happened yet, and so this is just a vacuum for the signal and vacuum for the idler. Now at time t equal to 0, the two photon state is given by this, where this is the initial state, that is a vacuum, and that becomes the final state, and this we can calculate by this evolution equation. Now here I should note that this is these are the vacuum signal and vacuum idle mode. So of course I am not putting any other label because all these frequencies are possible, and at the end of the interaction then one obtains this state. Okay, now since parametric down conversion is a very weak process, we will actually see that we will have at least this process is so big that for every 10 to the 9 photon we will have one pair of signal idler get down converted. So this process is actually quite weak, and so we can do a perturbative expansion of this expression. So if we do a perturbative expansion, what we have is 1 plus this term, that is minus IH bar integral HT, and then plus the square of this term minus IH bar HT acting on this vacuum signal vacuum idler. We see that the first term, which is the initial vacuum state, this 1 acting on vacuum S vacuum I just gives the vacuum initial state, which is vacuum S vacuum I. The second term, which is minus IH bar integral HT dt acting on vacuum S vacuum I, is this. So that is the second term. Now we will actually see that this second term gives rise to two photon state. Similarly, this third term, which has a square here, that will actually give rise to 4 photon states, but for now we are not interested in 4 photon effects, we are only interested in 2 photon effects. So we will just study, we will just stop at this at this term in this perturbative expansion. So this is the 2 photon state, and this is the expression that we have for it. Now we have already derived the Hamiltonian for this one in the like few slides back, and that is the expression that we have here. So the 2 photon state that gets produced at the exit phase of this crystal or the nonlinear medium is given by this expression, this long expression. So here we have an integral over this interaction time. This also involves an integral over the length of the crystal, and then it has these 3 different frequency integrals, and we have this creation signal operator and creation annihilation operator acting on the vacuum, and we can see when this creation signal operator acts on this vacuum state, it gives us a signal photon at frequency omega s. When this acts on this vacuum I mode, then gives the an idler photon at frequency omega I. Okay, now we'll assume that the interaction time t interaction is much longer compared to the time scale over which down conversion takes place. So of course this t interaction is basically the time it takes for light to travel through this crystal, and usually these crystals are few millimeter thick. So this is not a very long time, but still we assume that the time scale over which the down conversion actually takes place is much shorter, And this is because when the nonlinear medium absorbs this pump photon, this doesn't go to a real state, this is just a virtual metastable state, and the time scale over which the absorption and then the subsequent two emissions that happens is actually much smaller than the time it takes for the light to travel through the crystal. So this T interaction, that interaction time, can actually be assumed to be much longer. And as a result, the limits of this time integral we can actually put to minus infinity and infinity. And as a result, this time integral, which involves this is the only time integral we have, omega s plus omega I minus omega p. This time integral we can then write as just this delta function, delta omega s plus omega I minus omega p. So if you now write it for this, this is what we get, that's the delta function. And if we now integrate over this omega s integral, this delta function will go away, and then we will be left with this integral. So this is the two-photon state produced by parametric down conversion, and this is right at the exit phase of the crystal. Okay, so that's our two-photon state. Now let's rearrange it, and then we can write this as this. This is now just a double integral, and this integral over z we are just writing it as this phi, and this phi is called the phase matching function. This is just rewriting this integral over here, and this integral over z, that is the length of the crystal, we are writing it as a phase matching function, and in this this term is z dependent, and so this just comes over here. This phase matching actually decides how efficient is this down conversion process. If the phase matching is close to 1, then this is a very efficient process. If the phase matching is small, then that reduces the efficiency of down conversion. And we will actually, in the next lecture, we will look at in detail actually as to what affects the phase matching, how to control the phase matching, what is the effect of the thickness of the crystal on the phase matching, and as a result on the down conversion process, and what is the effect of other pump parameters on down conversion process, and so on. So this we will do in detail. So for now, it's just that the phase matching decides the efficiency of the down conversion. Okay, so that's our two-photon state. I just want to kind of point out that this also gives us an entangled state. So I'll just quickly illustrate that here. So for that, let's just make these change of variables. So here we have this state in terms of omega s and omega I, but let's take these two variables, omega p and omega d, where omega p is omega s plus omega and omega d is omega s minus omega I. So if we make this change of variable, then the two-photon state we can write as like this. So this is just a change of variable. This is this v, the pump amplitude, now is a function of just omega p. The phase matching, these are the variables for phase matching. That's the signal state, which was just omega s. Is now omega p by 2 plus omega d, and this is the state of the idler. So this is the two-photon state in this new set of variables. Now suppose if the pump is a monochromatic field, that the pump is just a monochromatic field of frequency omega naught, then this integral over omega p can just be replaced by a number over here, just v naught, and this term then just comes out with just omega p getting replaced by omega naught, and we are left with just this single integral. And this is the signal state, and this is the idler state. Now we can see that this integral, which is single integral, so we can see that this state is not separable. That means it cannot be written as a product of a signal state and idler state, because this is the signal state, idler state, and then integrated over. So this cannot be written simply as a product of the signal idler. So this is a state that is inseparable in terms of signal idler. Hence, this is an entangled state. So inseparability is the main criterion for the state to be entangled, and we can right away see that this represents an entangled state. But at this point, we are not going to go into the details of two-photon entanglement. Our aim is to first study two-photon coherence, two-photon interference, and then go towards two-photon entanglement. So in the next lecture, we will study this phase matching function in a bit more detail, and then we go towards two-photon coherence and two-photon interference and try to explain that using the same intuition that we had for the classical field as well as for the one-photon fields. So for this lecture, we will stop here. Thank you.